All right. So just to give you a little background, because this is our first two lessons together. I hate that I have to do this virtually. Again, I apologize, but it's important for me to be there while my husband has surgery. So this is not how this is normally going to go. Normally what will happen is, as we go, we're talking about Unit 1 polynomial functions really all the way through the whole program. Just skip that one. We'll come back to that. This is the first unit, is polynomials. What we're going to be looking at today is what is a function, input-output values, how a function increases and decreases, some things like that. Okay, so we'll be looking at those guys. These are our student concepts. They're at the beginning of every unit. So you'll have a chance to look back through them and see, do I understand what AP wants me to understand? It's a good checklist that we'll go over as we finish a unit and you're studying for your test. So the way this will work is that when you come into class each day, you'll have an ACT warm-up, which you've had already. But after that, you're going to have an activity that looks like this guy right here. Can we predict maximum heart rate? This is activity number 1. I'm not normally just going to do notes for you. You're going to be looking at these first. I'll give you 10-15 minutes. You'll be working with a partner, and you're going to do whatever you can of this so we can see where you're at first. And then we'll come back together after 10 or 15 minutes, talk about it as a class, fill in the things that you need to know. There will be fill-ins, so you may want more than one color. You may want a highlighter. You may want to do the first work in pencil and then have a pen or something or a marker, felt tip to put in extra notes and stuff so you know what you did versus what we did together. All right, and I'll be doing that a little bit today. I'm going to start in blue here. So normally what you do is, can we predict maximum heart rate? All right, what are we looking at here today? Understanding heart rate can be an important tool for your own personal exercise training and for monitoring your cardiovascular health. One measure that is often calculated is your max heart rate, or HR max. Your maximum heart rate depends on your age. This is a very telling statement here. Your max heart rate depends on your age. Hang on a sec, guys. All right, so let's keep going here. What you're going to see is that phrase right there, your maximum heart rate depends on your age. What that's telling you, and we're looking here, we have heart rate and age also, and we've got a graph just below that, is that we have variable. And in any function, we're going to have a variable that we plug in and an output. In other words, an x that goes in, that's an input, and a y that comes out, which is our output. For every x, we get a y. So we have to identify those things first. All right, so how do we identify those here? The maximum heart rate depends on your age, tells me that my heart rate here is the outcome. So this is my output, heart rate. And since it depends on my age, it is the dependent variable. All right, now the age then would be the thing that is the input, or my independent variable. You should remember these from Algebra 1 and Algebra 2. So we've got a dependent variable and an independent variable. So now as we get this table here, we need to look at that. We know age is our independent variable. That's almost typically always X. Our heart rate in beats per minute, that's BPM, is our output, which we are not going to call Y. We are going to actually, since we're looking at a function, we are going to call this f of x. In other words, that is the same thing as y. In other words, f of x, and we can put that to the side, f of x is equal to y, because we know that in function terminology. So if our age is 14, that's going to give us a heart rate, max heart rate of 206. If it's 18, 202, and so on, these all represent coordinate pairs as well, which we can then use to graph. Okay, so now let's go back to this and let's actually see if we can answer some of these questions. It says describe the relationship between age and maximum heart rate. So what do we see happening here? At 14, your heart rate is 206. At 25, it's 195. At 50, it's 170. At 72, it's 48. In other words, as your age goes up, your heart rate, your max heart rate, goes down. Now, you can't just write it that way. I know it's tempting to, but you've got to get used to actually stating these things in sentences. So what do we say? We're going to say, as a person gets older, their max heart rate decreases, goes down. Let's use decreases. I like decreases. Good math word. So it says predict the maximum heart rate of a 35-year-old. Explain your method. Well, let's see what's going on here. How could we do that? Well, at 35, that's somewhere between here, so we know it's got to be somewhere between 195 and 80, doesn't it? 25 and 40. So what's happening here? Let's figure out, this difference is 15, so this is a difference of positive 15, and from 195 to 80, it's going down by 15. Well, those are exactly the same. So what conclusion can we draw? For every year it goes up in age, it goes down 1 beat per minute, because we're seeing that. The comparison is up 15, down 15. So what we know is 1 year older leads to 1 beat per minute lower. So let's figure out from 25 to 35, that is 10. So from 25 to 35, we're doing plus 10. So beats per minute must go minus 10. So we started at 195, right? So what do we know here? Minus 10 equals about 185 beats per minute. So that would be the max heart rate for a 35-year-old. All right. So now it says the graph also shows this relationship. What's the max heart rate of a 60-year-old? Well, how do we find that? Well, the bottom down here says its age, so let's find 60 years old here, and we'll follow it on the graph. So at 60, we're going to go up to here, figure out what's going on, and then we're going to use that graph, our x, to then go over to the y-axis here and figure out what our beats per minute is here. So it tells us our heart rate max would be HR max would be equal to 160 beats per minute. Notice I'm putting units on there. It's important for you to do that. Now, in function notation, what we can do is, let's make sure we understand that function notation. This would be f of 60, because 60 is our input, isn't it? Heart rate of a 60-year-old, that's our age, it's our input, gives us an output of 160. So this is our function notation. Good to remember that. So now it says, what age would you predict for someone who has a maximum heart rate of 200 beats per minute? So now we're going to go the other direction. So let's look at this. I'll put it in green this time. 200, we're looking on the y-axis this time. In other words, let's talk function notation. We want to know f of what equals 200. So that's what we're looking for. So we're going to go over here at 200, go over from our y-axis to the function, and from there, go down to here, and we'll see that the age is 20. So x equals 20 according to our graph. So 20 years old. Always specify what that means. A number is just a number until you actually give some sort of idea of what it actually stands for. And when you're doing functions like this and you're given specifics, you've got to do that. So now it says write an equation that can be used to determine the maximum heart rate of someone who is X years old. In other words, we want to write this equation for anybody. All right. So let's write this equation. We'll do this one in black. So how do we do that? Well, we're given a graph. If we're given a graph, we know that a graph is equal to, we know y is equal to what? Y equals mx plus b. All right, great. I wanted to turn this black. There we go. Y equals mx plus b. So we need to know what b is. B is our y-intercept, isn't it? And this guy is our slope. So we can look at this function. Where's my y-intercept? My y-intercept is right here, which is at 220. So my b is equal to 220. Now, in this class, it really makes more sense. Y'all are used to doing y equals mx plus b. I don't want you to do that anymore. I would really prefer you write it somewhat better. In other words, what I want you to write it like is the following. I know some of you are yelling at me. You're like, Miss Steffi, what'd you do that for? I want you to do f of x equals b plus mx. Think about why I had you put the b first. Because that's where the function is starting. At the y-axis, when x is 0, that's b. So it really makes more sense from a real-world scenario to start with your y-intercept and then tell us how it changes according to the slope to get the next thing. So we know b is 220. So we're going to start this at 220. We know what the slope is, don't we? Didn't we just figure out what the slope was? You may not think it, but we did. Our slope at this point, m, we found it right here. We figured that out. This is my change in x, because remember my slope, and I'm not even going to do m anymore. We're going to use the word slope, because m could be a lot of different things. Our slope is going to be our change in y over our change in x. Well, what is our change in y over change in x? Well, number one, some of the things you can see here is, first thing you can see is that this thing is going down. So my slope is negative. So my slope is going to be negative, isn't it? Because my change in y was negative 15. We found that up there in our table. So this guy right here is my change in y. And my change in x, this right here is change in x. This is change in y. So my change in x was positive 15. So we found that for every 1 year of age, it went down by 1 beat per minute. So there's my slope. So minus 1x. All right. So what that means is really this is 220 minus x. Here's my function. F of x equals 220 minus x. So what do you think of reasonable values for your x in your equation? Okay. So what would a reasonable value be? In other words, can we go below 0? In other words, can you be less than 0 years old? No, you can't. All right, so reasonable values for x would be where? Starting at all right, something's going on here. Okay, so starting at what? So we're going to start at 0 and go to wow. My iPad is really freaking out right now. All right, so we're going to start at 0 and go to what? What is a reasonable age? 50? 70? I know some of you probably think 70, but the graph goes at least to 80. But what's a reasonable top age, a max age? Maybe 100? Some people live longer than 100. So maybe 110? Starting at 0 and going to 110 years old. Now it says explain. Why? Starting at 0, so age can't be negative, and 110 years old, most people don't live past 110 years old. Okay. So now, do you think it's possible to have a maximum heart rate of 100 beats per minute? Well, let's look. Now, if we go to our graph and look at that, that's kind of interesting. 100 beats per minute is going to go over here. So this goes out even further. It's not actually on our graph, so we can't use our graph for this. So what will we have to use? Well, looks like we're going to have to use our function, which is what we have. So 100 beats per minute. In other words, can f of x, let's go back to black, can f of x equal 100? Well, what does f of x equal to? It's equal to 220 minus x, so that's what we do. We set 220 minus x equal to 100 and see what it gives us for x. So we can actually use this function we've written to solve other equations. So now we bring x over to the other side and 100 over to this side, so we're going to subtract 220 minus 100 and set it equal to x. So x is equal to 120. And what does that stand for? X is age. We found that up here. X is age. So 120 years old. Does that make sense to us? No. So do you think it's possible to have a maximum heart rate of 100 beats per minute? So our answer is going to be, the answer is no. So humans don't typically live to what? 120 years old. All right, so now let's talk about something. Let's start at this starting and ending range. If we're talking about reasonable values for x, what do we call that in a function? 0 going to 110 years old. I want you to think about it. That is your domain. So domain is all of your x values. So we set that as being from 0 to about, we set 110. Okay? So what would our values be for our range? And that would be our outputs, would be our range. So if x is 0, we have 220. We could go over here and say, okay, so for x to be 0, that would be 220 minus 0. So that would be 220. That would be the highest beats per minute. So that would actually go on this side. And if we have 110, then we're going to take 220 from this other side here. We're going to take 220 and subtract 110. So that would be 110. So we would have 110 on this side. So our range would be from 110 to 220, where our domain would be from 0 to 110. Okay? So now let's look at the last little chunk of this, and then we'll kind of condense everything we've learned here. All right, While the formula found is easy to use, researchers found to be less accurate for women. They proposed the maximum heart rate would be this function to estimate the maximum heart rate, okay? X years old. It says find H of 32. So we're going to evaluate this. In other words, when it says H of 32, it's asking you to evaluate the function. FCN is function. Evaluate the function. So H of 32 simply means plug in 32 where there's an X. 206 minus 0.088 times 32. Okay, so what do we get? We get about 177. You should be working this on your calculator along with me. 0.84. Okay. Now, what does that stand for? What does that mean? That means a 32-year-old woman, because this is where the interpret your answer in the context of this problem means. That's here. A 32-year-old woman would have a max heart rate of 177.84 beats per minute. Boom. Okay, so let's summarize everything we've looked at so far. That's what we'll be doing at the top here, functions and function notation. So what have we learned? Learning target 1. So learning target 1 says, a function describes the relationship between what? An x and a y, right? Or an x and an f of x. What are those called? X is an independent variable. Y is a dependent variable. All right. Now, if it is actually a function, this is important. What is the definition of a function right here? Each input maps to exactly one output. In other words, for every x, there's exactly one y, right? All right. Now, how do we evaluate a function? To evaluate a function, what do we do? We're going to find the output. For a given input. How do we do that? We did that 3 different ways, guys. The first thing we did was we used a table. Or a set of ordered pairs, right? The second way we did it was looking at a graph. And the third was using an equation. So there's 3 different representations that we can have here. All right, so learning target 2, doing a different color here. Learning target 2, what do we call the inputs? You look at your notes, set of inputs was the domain. And what is the set of outputs? And remember, the domain is the values where the function is actually defined, okay? What are the outputs? What is the set of outputs called? Yep, I know somebody probably said it. It's the range, isn't it? And the range is defined by the inputs, okay? That leaves us with one last learning target, one last thing that we learned. So this is LT number 3, and that's this. Function can be written as f of x, or we could call it a and b. F of a equals b, where a is our input and b is our output. Now your first part of your homework is going to be the check your understanding. You have 2 problems here that you need to work through. Problem 1 has 4 parts and problem 2 has 1 part. Okay, so normally we would stop and let you work on this just a little bit and then move on to the next lesson. We're going to go ahead and just move on to the next lesson. We can get through this. The next lesson and the next thing, we're going to look at changes in linear functions. It says, how much does it cost to rent a U-Haul? Of course, a linear function graph says what? Yeah, I hope you said a line. Linear meaning line. U-Haul is moving a truck rental company with over 20,000 locations in the United States. Customers pick up a truck, drive their belongings to their new home. The cost of renting a U-Haul depends on the number of miles driven in the truck. So right away, let's apply what we learned last time. So we should be thinking, okay, function, great. Cost of renting depends on the number of miles. So already we should be able to define an X, an independent variable and an dependent variable. So the cost is dependent because it says, so this is our dependent variable. And the number of miles driven is what it depends on. So this is our y, or our f of x. In other words, this is our x and this is our f of x, which is our independent variable. Okay. So it says the table below shows the relationship between the number of miles driven with a U-Haul and the cost of renting the U-Haul. All right, so the first thing we need to do is figure out if we're going to notice they've given us a table, but they've not given us a graph this time. So what we would want to do is we would want to be able to figure out what type of function this is. And oftentimes the way we would find it is to look at how the x and the y relate to each other. So let's look at part A. It says, what's the average rate of change in the cost of rental? When you see average rate of change, the first thing you ought to think is slope. Average rate of change is your slope, guys. Okay? So we have to figure out what the slope is. To do that, we're going to look at the change each time. So what's happening here? We've got 10 to 15, we're going up 5. And here, we're going up. All right? So let's see by how much. Let me see. We have 33 33.34, and we are going to subtract 28.89. We have a change of positive $4.45. Now be careful, because you don't know that these are changing the same every time. If you look and see, we've got it going up by 5 here. Okay, is it going up by 5 anywhere else? The answer to that one is a big fat nope. Here it's going up by what? This is going up by 10. This is going up by 15. And this is going up by 10. Okay, well, we at least have 2 of them that are going up by 10. So let's look at this change here. Oops, did not mean to do that. Meant to do this. Let's look at this here and this one here. So we want to see the change from here and then to here, and then the change here and of course here. So let's do that. So how does this change and how does this change? Well, 42.24 minus 33.34 is a positive 8.90. And if we take this other one, guess what you're going to find? Hopefully you're doing this. 8.90. So look, these changes for our change in y, for the same change in x here, if these are the same, guess what? These are the same. So guess what that means? That means that they are linear. So let's actually write that down so we remember that. So if equal change in input produces equal change and output, it is a linear function. So we know this is linear. So it says, what's the average rate of change in the cost of a rental between m equals 10 and m equals 25? So from 10 to 25, let's try that one. So from 10 to 25, we want the average rate of change. So that's going to be our change in y over change in x. So our change in y would be our change in cost from 10 to 25 would be here. So 42.24 minus 28.89. And then we have in the bottom, change in x is 25 minus 10. So we're going to get 1335 divided by 15. And that gives us $0.89 cents per mile. That would be our average rate of change there. Now it says, what's the average rate of change in the cost of the rental between 25 and 50? So let's do that in a different color. Let's do that in red. So from 25 to 50 and from 25 to 50. So rate of change would be change in y over change in x, because rate of change means slope. So this time our change in y would be 64.49 minus 42.24 divided by 50 minus 25. Okay, we're going to get 22.25 divided by 25 this time, but look what we get. 0.89 cents per mile. So what do we see? We have a constant rate of change. Constant meaning not changing. So right here, we know and a constant rate of change means it is linear. Okay? So now it says graph the points. Okay, so let's graph the points. What does the graph reveal about the relationship? So one way we can tell if something is linear is we can look at its rate of change, average rate of change, and see if it's constant. The other way we can do it, of course, is to graph the points and the values, and see if we get a line. So at 10, we have 28.89. At 15, 33. So right about there. At 25, it's now at 42. Oh, it's looking pretty linear to me. At 40, it's 55, almost 56. And at 50, it's about 65. So right about halfway. And look at that. Look what we have there now. What we see is that we have I'm going to use yellow to do this. We have a linear equation going through these points. If we do line of best fit, what we're seeing is this thing is going to be here. We've got something here. We've got a point here. Maybe I'll do those back in blue. We had a point here. We got one here and here and here and so on. So what we're seeing is this average rate of change. It is continuing on this way. It is not, however, continuing on the other way. So what we know is we've got a point right there as well. So what do we know? We know a constant rate of change equals a constant slope. Okay. So now, let's answer the next question. Graph the points. What does the graph reveal about the relationship between the number of miles driven and the cost of the rental? Well, we know the points make a line, don't they? So what do we know? The cost per mile, and that would be the slope, wouldn't it? In cost per mile, the slope, that's what we've been finding. Cost per mile. That is constant. That's what linear means, is it has a constant slope. Constant rate of change. Is the rate of change of the cost increasing, decreasing, or staying constant? Well, is it changing? How can we tell of what the rate of change is? Well, we would have to actually look and see what would the rate of change be. Okay, so for the same amount between these 2 points, that would be what we could call a second difference. Here, let's do a different color. That would be here. This would be, it went up by 10, but did the rate of change? This difference would be 0, wouldn't it? So is the rate of change of cost increasing, decreasing, or staying constant? Well, it's constant on any interval, okay? What was it? Staying constant, we knew it was 89 cents per mile. So now, if we take the rate of change, which we did up there, we did the second difference, what we call the second difference, which is the rate of change of the rate of change, was equal to 0. That's also a sign that it's linear. Okay? U-Haul charges all its customers a minimum base price regardless of how many miles they drive. What is that base price? How do we know? Well, what would the base price be? Base price, guys, would be right here, wouldn't it? This is how much it starts at. This would be the y-intercept. So, what's the base price? If we look at this graph, the base price is just slightly less than what? Slightly less than 20, but we need to know exactly what it is. So how do we figure that out? How do we figure out what that is? So we need to figure out how to find it. We do that by taking what we know is the rate of change. We know the rate of change is what? 89 cents. So let's think in terms of a function. Our function f of x is going to be equal to whatever that rate of change is. In other words, the y-intercept plus the slope times x. Awesome. So we don't know what b is, but we do know another point on that graph, don't we? What's the first point we know on that graph? Guys, look at the table up here. We know at 10 miles driven, we know what the cost is. So we can take that and put it here and here, can't we? Sure can. So let's do that. What we know is that at a cost of $28.89, oops, didn't mean to do it that way, $28.89, we don't know this, but we do know what? Slope was 0.89, and we know that our x, our cost at the time, was 10. Miles driven, I'm sorry, was 10. So let's figure out what b is from plugging into that. We find that b is equal to $19.99. That is the base price. So how did we find that? How did we know? We took the cost for driving. In other words, we took the cost $10 miles, didn't we? And subtracted it from what? The price for every mile. That left us with $19.99, which must be the base price. So now it says write an equation C of M for a cost of renting the U-Haul and driving it for M miles. Well, that's going to be easy to do now that we know. So we know that it's going to be C for M miles. It's going to be that base price. Well, what is that base price? $19.99 plus the slope, or the rate of change, which would be 89 cents per mile driven. Boom. We have an equation. So do you see how we took the stuff that we knew from the previous unit, the relationship between x and y, inputs and outputs, and now we've thrown in this idea of rate of change being constant for a linear function and looked at it, and we've kind of gone over all of the basics here. So let's wrap up. Let's wrap up in our little notes section here. Looking at, if you look over here, is changes in linear functions. So what did we learn? Quick notes. What we learned here, and let's do learning target 1 for this lesson, is that linear functions have a constant rate of change. We know that. Okay. Now, how do we find that constant rate of change? We take equal intervals of the domain, and they give us equal changes in the output. Equal changes in X give us equal changes in Y, right? So equal changes in X, these would be our domain, interval, give us equal changes in Y, which would be our range or output interval. All right. So what's learning target 2? If the rate of change is constant, then the second difference must be 0. In other words, we learned that the rate of change is constant. The rate of change of the rate of change would be equal to 0. All right, so what does that mean? Here's a hint, and this is giving you a preview of what's to come. That means lines don't curve. In other words, lines have no what we call concavity. All right. So how do we know something? What does this really actually look like? I want to go over here. You don't have to write this down unless you want to, but if you were looking at this at an X value and a Y value, just to be sure that you understand, if X is 1, Y is 2. If X is 2, Y is 4. If X is 3, Y is 6. If X is 4, Y is 8. So we have equal change in plus 1, plus 1, plus 1. Here we have plus 2, plus 2, plus 2. Okay, so this is my first, what we call our first difference. Okay, these are the same, so we know this is linear. All right, now if we go again to our second difference, here 0, here 0. This is what we're talking about as our second difference. If you still weren't keeping up, now you know. Second difference is here. If the second difference is 0 all the way across, then we know this thing also is linear. If it were not, if it were constant, if the first difference was not constant and the second difference was, that tells us it's actually quadratic. And you'll see that next time. All right. But that's what this means. So now let's wrap this up with our third learning target. So LT number 3. What does the slope of the line represent? What did we say it was? When you think slope, you should think, I hope you're saying it in your head, rate of change. And that rate of change for a line would be constant. Okay? Now, what does it mean for the slope? And we didn't really talk about this directly, but we did touch on it. If the slope, or the rate of change, is positive, in other words, it's greater than 0, what's happening in that function? It's a positive rate of change. That means that the function is going up. In other words, the function is increasing. What happens if the slope is then less than 0? Hopefully you're saying that the function is decreasing. All right, guys. You need to do these two problems and check your understanding. They're not hard. They're just asking you to do some things to apply what you've seen here and actually figure out things like at what rate. What are they asking you? If they're asking you at what rate, you should be thinking the word what? Boom. Yes, slope. Find the volume of the air remaining in the mattress. You've got to look at this guy right here and see that volume is your output, time in minutes is your input. So you're going to have to establish and figure out and actually apply that rate of change, just like we did in the previous one. Okay, we'll talk about this when I get back. And next time, I'm not going to give you the answers. I'm going to give you how does the food industry set prices, and you're going to have to actually work with a partner through this and see what you can come up with on your own first. All right, I will see you when I get back on Wednesday. Thanks, guys. Bye.